Hey everybody, Morgan here. So we're going to be talking about the first few pages of the lecture outline dealing with chemical kinetics. And this word kinetic right there, that comes from movement or molecular motion. And everything we're going to be talking about here really deals with the motion of molecules. Okay? So before we can start, I need to make a distinction between the words time and rate because a lot of people confuse these. So time is what we measure with a watch. And a rate is how a quantity changes. With respect to time. So to kind of simplify this, time is how long, and rate is how fast. Okay? All right, so we're going to use these words a lot in this chapter. Chemical kinetics, what is it? It is the study of the rates and mechanisms of a chemical reaction. The study of the rates and mechanisms of a chemical reaction. So really two parts. We're going to study rates and we're going to study mechanisms. Now a reaction rate is the change in concentration of a reactant or product with respect to time. And I think this is much easier to understand with the equation capital R equals delta C over delta T, which is like saying C2 minus C1 over T2 minus T1. It's a slope, okay? We're going to deal with this graphically an awful lot. So our first mission then really is how do we affect reaction rates? And we need to understand that we're always going to be talking about what is called an effective molecular collision. And that is one that produces a reaction. Okay? So, what are the factors that play a role in this? You know, how is it that a reaction occurs because of a collision? Well, what we say is they have to hit hard enough, okay, and in the right place. And very often we call this orientation. So pretty much the answer to every question in this entire chapter is they have to hit hard enough, and they have to hit in the right place. Now, we're going to look at 6 factors that can affect this, although almost all of the explanations are going to end up being the same. Temperature, which we said is molecular motion. So, if you raise the temperature higher T, they hit harder. And they not only hit harder, they hit more often. They're moving faster. So the collisions are harder, you have more collisions. That means you get more reaction. But you knew that from the kitchen, cooking. Okay? Concentration. More species present, means more collisions. Agitation. It's a fancy word for mixing. And really, it's not any different than talking about temperature. You're making them move more, they're going to hit more often, they're going to hit harder. Surface area, more places to hit. If I take a sugar cube and drop it in a cup of tea, it takes a relatively long time to dissolve. If I take a spoonful of sugar and drop it into a cup of tea, it dissolves almost instantly. More surface area, more collisions. Okay? Now, you may have heard about catalysts in biology, and most of what was said there is very biology-oriented, and we really need to look at a much bigger picture. A catalyst can lower an activation energy. It can also raise it too. So what we like to say is catalysts provide an alternate energy pathway. All right. We spend a lot of time on that later on. Finally, the nature of the reactants. Okay? Let's face it, some things react and some things don't. Okay? There's nothing you can do to speed up the reaction of helium because it's never going to react. So we just have to live with that. Okay? It's just in their nature. All right. Now, we're going to draw a couple of graphs here to try to understand energy pathways and that. We'll work on an exothermic reaction first. We'll put energy on the y-axis and we'll put time on the x, and it's going to look something like this. You've got your reactants over here, you've got your products there, and this right here is going to be called the activation energy. Okay? The distance between the reactants and the products, okay, it's really more about here, sorry. That is called the enthalpy change, or delta H, enthalpy. And up here at the very top, you have a transition state. And we'll get into all of these in more detail later on. Now, the really telling thing about this graph, the take-home point, is that the energy of the products is lower than the energy of the reactants, which means energy is given off, and hence that's why we call this exothermic, okay? And this is a reaction that would feel hot if you were holding the test tube. Now, for an endothermic reaction, typically looks something like this. Reactants, products, activation energy. The distance between the reactants and the products is still delta H. This is still the transition state. Now, here's the deal. This time, the products have more energy than the reactants, so that it is endothermic. Energy is going in. And this one would feel cold if we were holding that test tube. Okay? So what are the reactants? The reactants are what you have before the reaction. The product is what you have after the reaction. Which is why we also have to distinguish between the transition state. We'll also use the term intermediate later on for what happens in between reactants and products. And activation energy is the minimum energy necessary for a reaction to happen. And very typically, biology books call this the energy barrier, which is a decent term for it. Okay, so there you go. That's the first 3 pages of the outline. Hope you all are staying safe. This is Morgan signing off.